Hi, this video is going to contain the solutions for your 10-1, 10-6 multiple choice practice, and then a few problems selected from section 10-6 in the book. And I'll show you which ones when we get there. But the first part will have this 10-1, 10-6 multiple choice. So for the first problem here, we have for what values of x does the series 1 plus 2 to the x plus 3 to the x and so on converge? And if you imagine x being 1, well, certainly that doesn't converge. So, I mean, clearly these would have to be fractions. So maybe we could look at this. I think maybe the easiest thing to do, let me do this on a separate sheet here, is say that the series 1 plus 2 to the x plus 3 to the x plus 4 to the x dot 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 is really like a p, kind of an upside down p series. That's the same as 1 over 1 plus 1 over 2 to the negative x, right? A negative x on the bottom. So that's one way to think about it there. And a p series, very important fact, p series will converge if the p is greater than 1. Right? If the p is 1, then it's the harmonic series, and we're out of luck. But if it's anything bigger than that, then it will converge. So look, this is our p here in p series, so we need negative x to be greater than 1, which is the same as x being less than 1. Oops, I lost a negative sign, didn't I? Let's try that again. Let's multiply both sides of this by negative 1 times negative 1, and then I'll change the direction of that sign, so there we go, less than negative 1. So that's correct answer is B for that. All right. And that we did with our knowledge of p series. So for number 2, which of the following series converge? Always important here, the College Board, let me see if there are any problems like that on this one. Sometimes they ask questions about sequences, like a sequence converges if the terms approach some number, but a series converges only if some other criteria have to be true, right? So here, how about this series? Are the terms going to 0? Yes. In fact, this is a p series with p equals 2. So per our discussion right there, that one does converge, right? That converges. Hey, look, that's the harmonic series. And we know that that does not converge. How about this? Well, this is an alternating series. So if it's alternating, the only thing that has to happen for it to converge is that the terms have to go to 0, right? If it alternates and the terms are approaching 0, then that's enough. And these terms will in fact approach 0. That will get bigger and bigger and bigger. So this will also converge. So it looks like 1 and 3 converge. Number 3. Which of the following series are convergent? Same kind of question as number 2. And in fact, I think that this is the same, this is in summation notation. This is what the term's written out, but that's the same series, right? That's p series with p of 2. So we know that that converges. Likewise, hey, is this the same exact question here? This is does not, because that's the harmonic series. And then this one's a little different. 1 minus 1/3 plus 1 over 3 squared. That's alternating and they're going to 0, and whether you notice this or not doesn't matter, but in fact it's a geometric series, right? 1 minus 1/3 plus 1 over 3 squared. It's a geometric series with the first term of 1 and a multiplier of negative 1/3. So not only does it converge, we can say that it does converge in fact to 3/4. So a lot of these tests that we do, they tell us that it converges, but it doesn't tell us what it converges to. This one's geometric, so we can calculate that. So once again, looks like 1 and 3 converge. Number 4, well, let's see what's going on here. This is starting at n, so that's kind of weird. So maybe, when in doubt, or, anytime you see a sort of strange series, you might benefit, I think you will likely benefit, from writing out the first few terms. So let's go ahead and write out the first term. We're starting at n, so the first term would be 1/3 to the n, and then the second term would be 1/3 to the n plus 1, 1/3 to the n plus 2, and so on. So the thing we have to recognize here is that this is a geometric series. It's starting, this is our first term, and you can see here that to get to each successive term, we're just multiplying by another 1/3. So that means we have the sum of an infinite geometric series. The sum is the first term, 1/3 to the n, over 1 minus the multiplier, which is 1/3. Now that's 1/3 to the n divided by 2/3, which is the same as multiplied by 3/2. So it looks like C is our correct answer. Which of the following series converge? Another one of these. So let's see. This series is alternating, so the only thing that has to be true is that has to be, the terms have to be going to 0. And as n increases, these terms will in fact go to 0. So that does. We might just comment here. You think about whether it converges absolutely or conditionally. Why don't you pause the video for a second and think about that. All right, so this, by the limit comparison test, this will behave, since the highest power here on the bottom is 1, this will behave like the harmonic series, which means it will converge only conditionally. But since it's alternating, it does converge. How about this one? It looks like this, with this 3/2 to the n and 1 over n. 1 over n is the harmonic series, which does not converge. So if you take the harmonic series and you multiply all the terms by something that's getting bigger and bigger, like greater than 1, that definitely has no chance of converging. And then this one we actually saw in class the other day, although maybe we only did it in one of the classes. So this one is a tricky one, and we did it on the excellent advice of Ben Lariviere. We did this one with the integral test. So we said, well, we know that the integral test says that the convergence of this is bound up with the convergence of this integral. If this integral converges, then so does this series. And then I think Ben was inspired to do that because it looked like something that might work with a u substitution. If you make u equal to the natural log of x, then du is equal to 1 over x dx, and then that turns this integral into, let's see, I need my new u numbers, that'd be natural log of 2. Natural log of infinity still goes to infinity, however, tragically slowly, and that turns the whole inside into just 1 over u, right? 1 over x dx, that's my du, and then there's my natural log x. And we know that that's the natural log of u from natural log 2 to infinity, and that's equal to the natural log of infinity minus the natural log of 2, and that is going to go to infinity. So this diverges. So that was a little tricky. So it looks like 1 only. And this one. Alright. Now, if you want to look at your book, I'm going to do 5 problems that were assigned to you and then one other one that was not, because it just looks like it's might be a helpful thing that if we've seen before or not. So I'm going to do these problems. I'm going to do numbers 17, 29, 30, 31, 37, and 40. And I think that'll be a pretty good selection. And I think I also chose the only even problems. So everything else you can try to reconcile them with these examples, and you'll have the answers now for the evens. So number 17, we've got a series. The sum from k equals 1 to infinity, cosine k pi over k. Now that's weird. What the heck's going on here? So anytime you find yourself asking that question, let's write out a couple of terms. So the first term would be the cosine of pi over 1, and then the second term would be the cosine of 2 pi over 2 plus the cosine of 3 pi over 3, and so on. So, well, what's cosine of pi? Well, the cosine function, cosine of 0 is 1, the cosine of pi is negative 1. Cosine of 2 pi is back up to 1 again. Cosine of 3 pi is negative 1. So it looks like this cosine of pi thing is actually just doing the same job that this would do. It's just another sort of sneaky way of getting the signs to alternate. And looking at this, I don't know if we need to say anything else about this. I think we can, or I don't think we need to do any work. I think that we know that this series, now you haven't done this one yet, so why don't you think about what's the punchline here. We're supposed to decide if this is absolutely convergent, conditionally convergent, or divergent. You can pause and think about that, and think about the justification. All right, so this converges because it alternates. So we can say because it alternates and the terms are going to 0, but it only converges conditionally because if we take the absolute value of the terms, we know that that's the harmonic series, and that diverges. All right. So just, be on the lookout. You might see that again sometime. Never know. Number 29. Same directions here. We're supposed to determine the convergence of this series. Sum from k equals 1 to infinity of negative 1 to the k plus 1. There's our sign flipper, so it's alternating. And k factorial over 2k minus 1 factorial. Now, the first thing we need to determine is, do we think that the terms are actually going to 0? Because if the terms aren't going to 0, then no series converges. So we got k factorial on the top, and then 2k minus 1 factorial on the bottom. And I think looking at factorials like we did the other day, that this is going to get so much bigger, so much faster that, yes, in fact, this will. And you can think about how the k factorial on the top just like cancels out a bunch of the terms here, and then there'd be only a 1 left on the top, so these terms are most certainly going to 0. So now we will do the, oh, wait a minute. Yes, so we know that this converges. Sorry, I was thinking for a second maybe we didn't have to do the ratio test, but we do. So this definitely converges because the series is alternating and the terms, the individual terms, are going to 0. So we know it converges. The ratio test is going to conclude for us, that it either converges absolutely or conditionally. So we're going to do the ratio test on the absolute value of the terms. In other words, we don't care about the sign flipper here. So we're going to investigate what is the limit as k approaches infinity of the k plus 1 term. That would be 2, careful here, times k plus 1 minus 1 factorial, and then divided by the k term, which is the same as multiplying by its reciprocal. Okay, now we have to do some simplifying here. So that would cancel with that, leaving just a k plus 1 on the top. And then this, I think I need to simplify this. 2 times k plus 1 is 2k plus 2, right? If I distribute the 2 through there and then minus 1. So this is actually 2k plus 1 factorial is what we end up with here. And then I've got the 2k minus 1 factorial here. So what cancels out here? Well, 2k plus 1 factorial is 2k plus 1 times 2k times 2k minus 1, etc. So this 2k minus 1 factorial is going to wipe out everything from there down. So we're actually left with 2 terms in that because they were minus 1 plus 1. Those were different by 2. So we're looking at the limit as k approaches infinity of k plus 1 on the top and 2k plus 1 times 2k on the bottom. And this is an easy pre-calc limit. The highest power on the top is 1. The highest power on the bottom, if you distributed this out, would be 2. So that is going to 0. And what does that mean? That means that our series converges absolutely. Right? It means, and this is the absolute in the sense of absolute value, right? Even if you take the absolute value, even if it doesn't alternate, alternating makes it much easier to converge. This series, even if it didn't alternate, the absolute values of it, it would still converge. It converges absolutely. It does not hinge, it's not conditional on the alternating nature of the series. All right, there's 29. And number 30. Same directions. Thought I'd do this one since it was even. We could have an answer here. So we got negative 1 to the k plus 1. There's our sign flipper. And then we got 3 to 2k minus 1 over k squared plus 1. Right? So now we have to convince ourselves first that these terms are in fact going to go to 0. So let's see. When we plug in really, really big numbers, like if we plugged in, say, I don't know, 1,000,000, then this would be 3 to the 2,000,000 minus 1 over 1,000,000 squared plus 1. So the question is 1,000,000 squared bigger than 3 to the 2,000,000? How should we determine that? Well, that does not seem so super obvious to me. So I think what I'm going to do then is figure out, just take this and say, I really need to know here just what's happening to the terms. What's the limit as k approaches 0 of these? Are they actually going to 0? Because if they're not, then that's game over. This is divergent. And of course that's an infinity over infinity. So I'm going to go ahead and try L'Hopital's rule and see if that helps me. So that would be the limit as k approaches infinity. This is a good review of how to do the derivative of this. The derivative of that, the derivative of 3 to the 2k minus 1 is 3 to the 2k minus 1, right? Because exponentials, a number to a power, that's like e to the x, right? But there's a couple adjustments we have to make here. It wasn't an e here, so I have to multiply by natural log 3. And this wasn't just a k, it was 2k minus 1. So that means I have to multiply by the derivative of what's inside, right? And that's the what's inside. So that's the derivative of 3 to the 2k minus 1. The derivative of the bottom is 2k. That's still infinity over infinity, but maybe you see where this is going now. So if I do L'Hopital again, I think just one more time, that I've got the derivative on the bottom is just 2. This is just a number, 2 natural log 3 times, and then I have to take the derivative of this again, but the derivative of this is just itself again. So this, that's going to infinity, right? That limit, those terms are going to infinity. And what does that mean here? It means that even though this is alternating, these terms are going to infinity, so this diverges. It didn't pass the most basic test, which is that the terms have to, in fact, be going to 0. Alrighty. Let's see. Next, we're going to do number 31. The directions here say that each series satisfies the hypothesis of the alternating series test. What does that mean? That means that the terms are going to 0 and it alternates. And they want, for the stated value of n, find an upper bound on the absolute error that results if the sum of the series is approximated by the nth partial sum. That's a mouthful. Now, what that means is the absolute error, and when they say absolute here, make no mistake, that means absolute value, right? That sense of the word. The absolute error, that's what they're looking for, right? We know that if the series is alternating and the terms are going to 0, then the absolute error is less than the next term. So the absolute error of the nth partial sum, that's the sum of the first n terms, is less than the absolute value of that next term, right? Regardless, it doesn't matter if it's positive or negative, it's at less than the absolute value of that term. The way the College Board often likes to write this, we should get used to seeing, is they like to say the error, the absolute error here, that's the error or the difference between the actual sum and your partial sum. Right? That's a way of writing that absolute error. It's the difference between the real actual sum and what you got by being lazy and stopping after however many terms. That's less than the next term, the absolute value of that. All right, so in number 31, the series that they're giving us looks like the alternating harmonic series. The sum from k equals 1 to infinity, negative 1 to the k plus 1 over k. And they are asking us to find the error if the series is approximated by the first 7 terms. So in other words, we're looking for the absolute error of this approximation, the sum of the first 7 terms. Well, we know that since it's an alternating series and the terms are going to 0, that the difference between the actual sum of the alternating harmonic series, which is the natural log of 2, happens to be, but we don't need to know that yet. We don't know that yet officially. So the absolute error, the difference between the real sum, whatever it happens to be, and the partial sum that we get by quitting after 7, we know that that's going to be less than the absolute value of the 8th term. Well, what's the 8th term? The 8th term would be negative 1/8. Right? So the absolute error is 1/8. Now, in the grand scheme of things, if you're trying to get close, that's really not that close. So what that tells us is this series actually, it converges to its limit pretty slowly. And that shouldn't be a big surprise, considering that it's alternating harmonic. All right, so that's what that's about. Let's look at a couple more problems that have to do with this error business. Number 37, we've got this series, k equals 1 to infinity, negative 1 to the k plus 1 over the square root of k. We saw that in one of the multiple choice questions. That will converge, right, because the terms are going to 0 and it's alternating. It converges very slowly, even slower than the harmonic series, because we've got the square root of those denominators. And they want us to figure out how many terms so that the error, as it says here, we want to be accurate to 2 decimal places. And I think I talked to you in a previous notes video that if you want to be accurate to 2 decimal places here, you've got to be within a half of that place. So if we want to be accurate to 2 decimal places, that means that we want error that's less than 0.005. Right? So whatever decimal place you're interested in, you got to go one more and make that a 5. That's how we deal with that decimal place accuracy. Okay? So let's think about this now. We know that the absolute error, that's the difference between the real sum, whatever this sums up to, who knows what that is, but whatever it is, that the difference between that and the nth partial sum, we know that that is less than the absolute value of the next term, right? And we want that error to be less than 0.005. So I think what we need to do is figure out what's the term that's less than 0.005. So here, the absolute value of the n plus 1 term, that gets rid of the sign flipper, the absolute value of the n plus 1 term is just 1 over the square root of k plus 1, right? And we need that to be less than 0.005, which is 1 over 200. I think it's a little easier to deal with as a fraction, so that's what I'm doing there. Now, if we cross multiply here, that means that 200 less than the absolute value of k plus 1. We square both sides. We square that and then you double the number of zeros. That'd be 40,000 is less than k plus 1. So k would have to be greater than 39,999. So this is the number that we're looking for, right? And you know, we're looking for an n. I should have written here, instead of writing k, the n plus 1 term, if we plug n plus 1 in for k, I think maybe this would be a little clearer what we're doing here if we made those all n's, right? We're looking for that value of n. So n would have to be at least 39,999. That's a lot. That's how many terms you would need in this series to be accurate to only 2 decimal places. It gives you an idea how slowly this thing converges to its actual value. All right? So let's try one more problem that's like that. Last one in this video. Number 40. Find an upper bound on the absolute error that results if S10, so we're going to take the sum of the first 10 series, is used to approximate the sum of the given geometric series. And we're going to compute S10 rounded to 4 decimal places and compare this value with the exact sum of the series. So number 40, they're giving me the series this. It's a geometric series with the first term of 1 and a multiplier of negative 2/3. Right? So that'd be 1 plus 2/3 or 5/3, and when we do 1 divided by 5/3, that's 3/5. So that's the actual sum. And what they want to know, they want to compute S10, right? And we know since this is in fact an alternating series, we know that the absolute error, the difference between the real sum and the sum of the first 10 terms, that must be less than the absolute value of the 11th term. So they're asking us to find these two things basically and just kind of check this out and compare, since we know how to find the sum of a geometric series. So to make this comparison and see that it really works, we have to find two things. We have to find the sum of the first 10 terms, and then we also have to find the 11th term. And I don't know if you remember how to do this. There is a formula for the sum of the first n terms of a geometric series. I don't really expect that you remember that. So let's pretend we don't remember that, and let's just do it with our calculator. And I want to use a formula that you probably don't remember. So what's the sum of the first 10? We are just going to do it by hand, and I suppose you might just like to then write out those first 10 terms, and then we can find this while we're on the way. So let's see, maybe I can write that down here in the bottom. I've got 1 minus 2/3 plus 4/9, minus 8/27 plus, these are powers of 2 on the top, right? So that's going to go 16, 32, 64, 128, 256, 5, 12, is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I guess we should go one more because we need that 11th term. So that's 1024. Right? And now we need the denominators, which are powers of 3. So that's 81, 243, 729. Oh, what's that one? 3,000 and... Let's see, so 729 times 3 is 2187, and not 3,000. And then times 3 again, 6561 times 3, 19,083, and then times 3 again, 59,049. So there you go. There's our 11th term. And then they're asking us to, let's see, compute the sum of the first 10 rounded to 4 decimal places. All right, so this is going to be a pain in the butt, but I'm just going to go through and sum this series. Get the light a little bit better. There you go. Okay, so we got 1 minus 2/3 plus 4/9 minus 8/27 plus. At this point, you're like, you should use the formula. You don't care if we don't remember, but if you remembered it, you could use it. 2 over 243 plus 64 over 729 minus 128 over, this is what it's like to be an accountant, by the way. Really exciting. Plus, you'd push lots of buttons. Plus 256 over 6561. No offense to any accountants out there. Minus 512 over 19,683. And then we stop there because that's the 10th, right? This was the 11th term. So that's the sum of the first 10. Bam. Rounded to 4 decimal places. That would be 0.5896. Right? So I just put a squiggle in there. It's approximately equal to that. Okay, so now we can check. And we can say, so according to this statement here, this idea with alternating series and their errors, the actual sum, which is 3/5, that's 0.6 by the way, minus the sum of the first 10 terms, which is 0.5896 rounded to 4 decimal places, should be less than the 11th term, which is 1,024 over 59,049. Now that's hard to see if that's true or not, so let's work this out. So let's see. I've got 3/5 or 0.6 minus 0.5896, which is 0.0104. That's supposed to be less than 1,024 divided by 59,049. 0.0173. And sure enough, it is. The absolute error was less than this. So this would have been a reasonable cap. You could say with confidence, hey, if you're going to sum it this far, the error will not be bigger than this. And in fact, it wasn't. It was a good bit smaller, right? So that's what that game's about. Have a nice day.